So, good morning, everyone. I'm very excited to kick off today's session. The first speaker is Stephen Spallone. So, yeah, the floor is yours.
Okay, thank you. Thank you very much for the invitation. It's good to get out here and talk about my stuff with you all. So this is a talk on, I guess it's the combinatorics coming out of just the classical Lie theory. It seems like a classical question, but it was something I needed for my overall project, which maybe I can talk about much later. But I think it's interesting in its own right. So the title is Symmetric Polynomials of the Weights of a Lie algebra representation. It's joint work with my student Rohit Joshi. So let me start easily by just reviewing the notation and idea of symmetric polynomials. So we have symmetric polynomials. And we can think of this inside the ring, the polynomial ring with infinitely many generators. And it's the subring of the symmetric ones. So for example, I'll write E1 for the sum of all of these things. Oh yeah, so I want, what do I want here? I guess I can think of this as a power series. Okay, thanks, yeah. So for example, I could take the sum of everything, and I might write that as sum of xi equals 1 to infinity inside lambda. I have E2, sum for I less than j of xi xj inside lambda, and ek would be the sum of, ek would be the sum of over I1 less than I2 dot 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 ik of xi1 dot 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 xidk. Okay, and I should mention this nice formula. If I take the product over all I of 1 plus xi, I get the sum of these elementary symmetric polynomials. Sum from k equals 0 to infinity of epsilon k, and we'll take epsilon 0 to be 1. Okay, we also have the power sums, okay, similarly defined as, so pk would be the sum I goes from 1 to infinity of x sub I to the power k. That's also a symmetric function. Okay, and when R is a commutative ring, and I have some finite multiset on R, okay, so some sequence with maybe with multiplicity, I can evaluate any of these symmetric polynomials with infinitely many variables. I can kind of specialize it to n for any of these things. For example, ek of R would be, I take ek of R1, R2, dot, 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 Rn, and I just put zeros in the other coordinates, and then I can evaluate it. Okay, so we can recall that of course, it's classically known that lambda is generated by these EIs. This is a polynomial ring in the E's. It's also a polynomial ring in the P's. Okay, in particular, you can get one from the other. E1 is P1. I'll mention E1 squared is P2 plus 2E2. And from that, of course, you can solve for P2 in terms of the E's and E2 in terms of the P's. Okay, so, I'm sorry, what? Infinite sums of all of so what you want? Yeah. Yes. So I think. Okay, yeah, sorry. Okay, thanks. All right. Okay, and generally there are formulas relating the E's and the P's. There's a formula from Newton which gives you, maybe I'll write down, so for example, n factorial En is the determinant of P1, P2, P1, Pn minus 1, Pn minus 2, Pn minus 1. I'll put a 1 here. Okay, so there's a straightforward but a bit intricate formula. P1's all the way down here for the En in terms of the P's. Okay, anyway, so that's my brief introduction to recollection of the symmetric polynomials. Now let's let G, so I want to talk about weights of representations. So let's let G be a reductive, let's just say complex Lie algebra. And inside that I'll have a Cartan subalgebra. I'll fix a Cartan subalgebra. And so, for example, you can think of SLN, little SLN, which is the matrices of trace 0, the n-bind matrices of trace 0. And then this has inside it this torus of diagonal matrices with trace 0. And I'll take phi and v. I'll write phi for finite dimensional complex representation of G. Okay, so when I restrict phi to t, I get a sum of weights. So this is a sum of various kind of irreducible representations of the t, which will be one-dimensional, called the weights. Okay, so T star, I of course mean the linear dual of T. Okay, so it's a sum of various weights. And typically they come with some multiplicity. And so I'm going to think about a multi-set of weights associated to this representation. Okay, and so basically I want to talk about evaluating these symmetric polynomials on the multi-set of the weights. But to do that, I need a ring. Okay, so I'll take the symmetric algebra. Okay, so I'm going to put fancy S, blackboard bold S, to be the symmetric algebra of the T star. Okay, and so then that would be my commutative ring. And then I can put, all right, EK of phi for EK of the weights of phi as a multiset. Okay, and that's going to be living inside the S. Okay, so I hope that's clear what I mean by that. And similarly, I'll have pk of phi, which will be pk of the weights of phi. And I can be a little more explicit about that. I'll write this as m phi of mu times mu to the k, sum over the mu, I could sum over all mu. And this is again a member of S. Oh yes, this is, okay, this is the multiplicity of mu inside the restriction of phi to t. Okay, so this is kind of the problem, is to figure out nice formulas for this. Let me quickly just write, it's kind of a convention, but it should make sense if you take the power sum from this formula. So I'll write for the zero power sum, just it's the sum of the m phi mu's. And of course, that's the degree of phi. Okay, so that's the basic question, is can we find formulas? How does one go about computing these things, the power sum and its equivalent, because of this equation. So I'm going to just show you how to find the power sums, and because of this equation, I will thereby also get the elementary functions, which are the ones that I'm really interested in. Okay. Okay, so the essential case is when, yeah, the multiplicity of, not monomials. Yeah, I guess I'm mixing a couple words here. So yeah, m sub phi of mu is the multiplicity of mu inside the restriction of phi to t. Okay, so the essential case, let me suggest a reduction. Okay, of course, if phi breaks up into two parts, the power sum of the sum is the sum of the power sums. But why do I think I can reduce to G simple? Well, if phi1 is a representation of G1 and phi2 is a representation of G2, and I form the external tensor product, I'll call that phi, of G1 plus G2, then it's easy to see that the kth power sum for phi is a sum over I plus j equaling k of k choose I and j, pi of phi1, pj of phi2. Okay, so because of this, and the abelian case is easy as well. I feel like all I need to show you is how to do the case when G is simple, when it can't be broken up into a sum of things. So I started with reductive, but I really mean semi-simple and indeed simple. Okay. Okay, so now we have, so now that I'm doing irreducible, I have some highest weight. The irreducibles are parameterized by the highest weights. And I might want to know how this depends on the highest weight. Okay, so I can take, I'll be writing phi lambda, where lambda is a highest weight of phi. And my goal is to find a formula for pk of phi lambda in terms of lambda. Okay, so I'll start with an example, but that's the goal. That's what I'm going to try to deliver. Okay, let's look at SL2. Okay, so for G equal SL2, I think I already explained the torus, but it's this. Well, really, it's just matrices of this form. I'll define mu naught and T star by putting this equal to 1. I can kind of normalize something there. And I'll take phi to be phi L, the irreducible representation of degree L plus 1. So L will be a non-negative integer. Okay, well, the weights of phi L, of course, this is all very well known. The weights, you might write it like minus L mu naught, minus L plus 2 mu naught, dot, 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 L minus 2 mu naught, and L mu naught. Okay, so in this case, there's no multiplicity. Everything has multiplicity 1. And this is the highest weight. Okay, so now this is kind of an easy problem. I've laid it all out. All I have to do is take the powers of this and sum them. So let's see what we get there. Okay, so pk of phi L okay, so when k is odd, they cancel. For example, the sum of all these weights is 0. It's kind of anti-symmetric. Let me go ahead and do the case k equals 0 separately. Okay, and then the interesting case is when k is even and bigger than 0, then of course its power sum is the sum, it's the sum of maybe the k. Yeah, let me tell you what epsilon is. Epsilon it's just L mod 2. So it's 0 or 1, depending on whether L is even or odd. Anyway, that's just some way to write it. Okay, so this is, of course, I can use something called Faulhaber's formula. Okay, so this is, of course, something we can get a polynomial formula in L for. Okay. So if I let sk of n be the sum of I to the k, this is, of course, a classical result. Wikipedia says due to Faulhaber is a polynomial of degree k plus 1 in n. And I'll just say Faulhaber. Okay, so I can use that. Of course, here I have to pay attention. So for example, if L is even, right, then I can just pull out a 2 to the k, and I'm getting sk of L by 2. So the most interesting line here, the last line, is to the k plus 1, sk of L over 2, and then the mu naught to the k. Okay, so even here there's something a little bit interesting. So it should be pretty, I hope it's pretty clear that that's the correct formula when L is even. It's also true when L is odd, which you might think of as maybe a non-trivial statement, right? Because I can't. So I'm taking this to be this polynomial given by Faulhaber, and I'm plugging in L by 2. I'm not adding half, I'm not taking powers of half integers. Or I mean, I'm not taking it up to L by 2. That wouldn't make sense. Anyway, so even there's something a little bit interesting. So what did we learn from this example? Well, we learned that it's a pk is a polynomial function in L. Okay, so I just want to emphasize that. And L was kind of the highest weight of the thing. One of my goals in this is to generally show that if I fix a k, then the pk of phi L is a polynomial function in lambda, which is maybe not obvious. Okay. Yeah, yeah. So you see that it's a bit non-trivial, right? Okay, so I'm going to later show that this thing's a polynomial. So maybe okay. So that's okay. So when L is even, so also when L is odd. So I'll put that up. I'll make that. I'll give an instead of explaining it, I'll say it's interesting that that's also true when L is odd. Later, I'm going to show this thing is a polynomial, and so a polynomial function which agrees with this on infinitely many points has to be a polynomial. So I do it in a tricky way. Okay. Honestly, I suspect there's a clever person can prove that directly. I'd be interested to hear. You can imagine doing this by doing some adding and subtracting using Faulhaber's formula. But then there's some identity that needs to be proved, and it's a bit non-trivial. Okay, so yeah, good question. Okay, so anyway, so polynomial. So at least in the case of L even, we can see it's a polynomial. Okay, let me quickly mention P1, just to get it out of the way. Okay, so now that was SL2, and now I'm going back to general G and phi. Okay, so what is, this is just something a little bit cute. Okay, so what is P1? It's also E1. It's the sum of multiplicities times mu. And notice this is in T star itself. It's degree 1. And can anyone guess what this is? There's a nice interpretation of this. Okay, we can talk about close differential formula a little bit later. This is not that. So this is the trace. Okay, so if I take T going to G, going to GLV, and then I compose that with the trace, that's a member of T star. And if you think about it, right, because when I diagonalize this thing, I'm getting mu's down the diagonal so many times, and I'm just and this is asking to sum that diagonal, so it's the trace. So this okay, so it's P1 of phi, by the way, is the trace of, say, I'll write it like that. In particular, it vanishes whenever G is semi-simple. Okay. Okay, so yeah, you were mentioning the formulas for this. Okay, so it's a good question to ask, why don't I just open up a book on so many formulas for these multiplicities? So if I know the multiplicities, if I had a nice formula for the individual multiplicities, then I should just be able to just use that to somehow put that into this thing, take the powers, and thereby compute pk, right? That's a reasonable thing to expect. And so there are algorithms that will give you these multiplicities. So I'm talking about the general problem. How would I do this in general for pk? There's something due to, I think Constant has a formula involving some kind of partitions of how many ways you can add simple roots together to get your weight. And then there's I think it's a recursive formula by Freudenthal. But these formulas they're difficult, and they don't just package together nicely to give you a formula in the way that I want. That's why I wrote the problem the way that I want. I want a formula, something like a polynomial formula in terms of lambda. So to say it a different way, okay, so going back to P0 is the degree of phi. Okay, and how do you find the degree of phi lambda? The answer is not go read this algorithm of Constant and this complicated partition function and concatenate all those directions and that's your formula. No, there's a very nice formula called the Weil dimension formula. Okay, and it's clear from the Weil dimension formula that it's a polynomial. Okay, so even though in principle, and the SL2 example may be a little deceptive in that it's very easy. But in general, these things are something we don't really have a nice formula for the m's in a way that would allow us to compute these symmetric functions. Okay, so we need to think about the Weil dimension formula and the Weil character formula. So somehow when you put all these things together, the individual multiplicities are perhaps incomprehensible in some sense, but when you put all of this package together, I'll show you that you can do something. Okay, so yes. Okay, so let me write down, so the Weil dimension formula comes from the Weil character formula. So I want to spend a minute, write down the notations for the Weil character formula in a way that we can then do a trick to get these PKs. So I'll use the notation which is in Humphreys. Okay, so I need to introduce another object. Okay, and this is the group algebra on the additive group of T star. It has a basis. I'll write the basis as E mu, as mu varies over T star. And so it's the group algebra for this infinite group. And so the multiplication is like this. So it's a ring. Okay, so if I have a representation, I can form CH of lambda, which is, again, a sum over multiplicities. But this one sits inside this group algebra. Okay? So it's a different place with different kind of multiplication. Okay. So this is called the character. And if your representation was the derivative of a Lie group representation, it wouldn't be hard to get the literal character from this using exponentials. Okay, so anyway, so that's one ingredient. There's one definition, part of the Weil character formula. We also have For a mu inside T star, we have J of E of mu, which is the sum over the Weil group. Weil group appears. Okay. So this kind of alternating sum over the orbit of E mu. I'm sorry, that should be a lower mu. I guess this just doesn't matter, actually. Just a definition. Anyway, so the Weil character formula is J of E lambda plus delta, J E delta times CH of E lambda. This multiplication is happening in this group algebra. Oh yes, delta here is, as usual, half the sum of the positive roots. Okay, so that's probably very familiar to many of you. Okay, so now, so what am I going to do? I'm going to take this formula and I'm going to apply a homomorphism to it. Okay, so you have C algebra hom, which I'll just call F. Okay, so this is my group algebra, multiplication like that. This is a commutative ring that we were talking about before. It's the symmetric algebra over T star. And power series, PRC is an X. Okay, so I can define it by requiring that Fe mu of this basis element is 1 plus mu times X plus a half mu squared X squared, and so on using the exponential power series. So I can write that as E of mu times X in this power series ring. Understood in that way. Okay, so I get an algebra hom. So this was my Rohit's idea. Okay, so when you do that, so I'm going to apply to the Weil character formula. And we have to do a couple calculations. Okay, so if I apply this C algebra homomorphism defined on the basis like this to this character, what do I get? So it's F E mu E mu, and that's sum xi over I factorial m phi of mu, mu to the I, and that is the power sum. Okay. Okay, so I noticed on the poster I should be talking about generating functions. So this is an exponential generating function for Pn of E lambda. Okay. All right, similarly, f of j e mu is sine of w times e to the w mu x. Okay, so this is a generating function for something else, which I'll call fk of mu. Where, and let me put that here. Fk of mu is a sum over w in the Weil group, sine of w, w mu to the k. Okay. Okay, so what do I get from this? So this, all right, so this is exponential generating function of fk of mu. Okay, so finally, so this will be an important definition. So applying f, this ring homomorphism, to this equation here now gives me an equation between exponential generating functions. So f of this gives exponential generating function of fn lambda plus delta is the exponential generating function of fn of delta times the exponential generating function of pn phi lambda. Okay, and so therefore, if I know this well, then I know the exponential generating function of the Pn of phi lambda by just simply dividing this. And of course, I can read off the Pn of phi lambda. You know, in practice, there's a recursive formula for the power sum functions in terms of these interesting functions. Okay, so by using Weil character formula in this way, I've reduced the computation of the power sums to the computation of these interesting things here, which don't depend on lambda. Okay, so I guess I can even right now, I can make some observations. Okay, so I want to know what this thing is like as a function of lambda. Well, this is constant. Okay. This, if I plug in lambda for mu, it's obviously a polynomial function in lambda. Right? I mean, fk of mu, in the appropriate sense, is a polynomial function of mu, because each of these things is just raising to the power. Okay, so maybe I'll make that note right here. So already, so we know that now that, let's say, lambda to Pn of phi lambda is, I'll put it in quotes, because you have to interpret it the right way, is polynomial. Okay, so already we have that, and that justifies, that's a very long-winded way to answer the question of why, for the Faulhaber sum, if I plug in the odd number, I get the same formula as for the in the even case. Anyway, okay, so good. Okay, so now I just want to address how to think about this. What do we do with this? Can we calculate some of them? Okay. As a very, very kind of interesting object. Okay, I'll copy it again. So fk of mu, sum over w, sine of w, this w mu to the power k. Okay, so the basic observation is that this is I have this phrase anti-W invariant in the sense that fk of W mu is equal to sine of W. Maybe I'll put W naught so we don't get confused. Of fk of mu. Okay, so it's an anti-W invariant. But yeah. Yeah, so I'm defining it on a basis and I'm extending it. Yeah, extend. Yeah. Sorry, are you here? Yeah, I mean, one has to, one notes that I think you have to check that f of e mu1 times e mu2 is equal to f of e mu. That's a homomorphism kind of on this subgroup. That has to be checked. Yeah, but it's basically because it's exponential, because of the properties of exponential functions. So that's right. I'm kind of skipping a certain amount of detail. Yeah. Okay, thanks. Right. Okay, so this thing is anti-invariant. So that's interesting. How many anti-invariant polynomials are there? Say on T star, right? That's an interesting question that should be classically known, and it is. Okay. So I guess it's a good time to mention this discriminant is defined by d of mu so this product over the positive roots of the pairing of mu with alpha check. And this is also anti-W invariant. Okay, so this is a classical, like it occurs in the Weil dimension formula. I'll call it a Weil discriminant. Also anti-W invariant. And it's a basic fact that every anti-W invariant function on T star is divisible by this D. So this is part of the classical theory of the Weil character formula. Okay, so in fact, every anti-W invariant function is divisible. So all anti-W invariant functions on T star, or maybe I should say polynomial functions, are divisible by this D. Okay, so I should divide by the D and I'll get a symmetric polynomial. Okay, but already, okay, so this thing here, so this is inside S and it has degree n. It's a polynomial of degree n, where n is the number of positive roots. Okay, as a function of mu, it's obviously the number of positive roots, which we write as n traditionally. Okay, so already we can see something. Okay, so therefore, if k is less than n, then fk vanishes because it's divisible by something of degree n. Okay, so it already vanishes in that case. So for k bigger or equal to n, I might write fk is d times fk prime. I'll just use fk prime for a notation of the division of fk by d. Okay, and so this fk prime is a W invariant function. Okay. Okay, so let me just lay out, let me just kind of sketch out where we can go with this. Okay, so maybe I'll emphasize now that G is simple. Okay, so Fn of mu, it's going to be a constant multiple of d mu. And it turns out to be n factorial d of this mu, d of delta, product of all the roots. So I just have a couple minutes, so maybe I'll just assert that you can prove the Weil dimension formula from this. So you can take this generating function, these exponential generating functions, you start the sum at k equals n, and compare things of degree n. How do I compute this? Well, I know that it has to be a constant times d mu because it's going to be a degree 0 thing. And to compute that constant, all I need to do is plug in 1 mu where I can compute things explicitly. So that's how one gets a formula like this. Fn, it turns out Fn plus 1 of mu equals 0. Fn plus 1 is just 0. That's related to the fact that on T star, there are no invariant W invariant functions or polynomials. Only the 0 one. Okay, now Fn plus 2 of mu. Then again, there's just one dimension of a quadratic W invariant polynomial, and that's basically the norm. Basically the norm. You know, the sum of the squares of things. To be more precise, let me just give you the whole formula for Fn plus 2. Whenever I have a norm here, it's the killing form. Okay, and so this is the formula for this Fn plus 2. So from this formula, you can deduce, find all of the P2s. You can find all of the second power symmetric function. Okay, and let's see. All right, so I could write down the formula for P2 in terms of this. Let me just tell you, I just have a couple minutes. Let me just mention the what should I mention? I guess, okay, so we've also computed F6 and F7 for G equals SL3. And since I'm a little at the end of things, I'll just assert that. And basically, what is the method? Well, there are tables of which polynomials on T star are symmetric, of which degrees. For a given degree, you can, in principle, write down a basis of the symmetric functions of those degrees. In a book like in Humphrey's book on Coxeter groups, for example. That can be found. And so you have a basis. And then just like if you know the theory of modular forms, there's a lot like this, where you know something's in this space, you know a basis for the space. And so by checking a couple points, you can figure out the coefficients exactly. Okay. So that's okay. So finally, in principle, and it is a bit difficult, but you know, one can do it. In principle, one can figure out these FKs by using this invariance theory, and from that deduce the PNs, and from that get any symmetric function on these things. Okay, so why am I interested in symmetric functions on these spaces? I guess I'll just quickly say that. It's because I'm interested in something called Chern classes of representations. And if I have G a topological group, maybe a Lie group, say it's a Lie group, and I have a representation, there's something called the Chern class, which sits in the appropriate group cohomology for G. And if I restrict that to the cohomology for a maximal torus, then this thing is equal to the C of pi restricted to T is equal to the product of over the mu's of 1 plus mu m to the power mu, which is the total elementary symmetric function for the derivative of pi. And so that's just in case you're interested, what my direct reason was for thinking about these things. For any pi what? Oh, member of, sorry. Member of, yeah. Anyway, so that's of course a long story that I can give on another occasion. Okay, so maybe I'll end there. Thank you for your attention.
Thank you, Stephen. Are there any questions?
So this thing you're doing reminds me awfully of operation called Platter.
Okay.
So, have you looked at the?
Not at all.
Okay.
Okay, all right. That's mysterious. Okay. Yeah, well, thank you for your question. That gives me a couple more minutes to talk. No, I'm just kidding. Let me see. So I wrote it down. Yeah, so what you do. Okay, so I start over here. So I'm going to start with this formula here, this. Okay, and then I'm going to compare x to the n coefficients, and that gives me Fn of lambda plus delta equals Fn of delta P0 of phi lambda. So now this thing here is the degree. So degree of phi lambda is d of lambda plus delta over d of delta. Okay, there's a few things cancel here. Yeah, okay. Okay, yeah, so this is a kind of a generalization or a stronger use of the Weil capture.
Interpretation also for Pn, P lambda, like P0 is a dimension. What's the interpretation of these values?
No, but I think only for P0, P1 do I have. I mean, the E's are, the EKs are represent the Chern, let's say the Chern class of the representation. So it's related to topology in that way. But I don't have much as cool as trace and trace and dimension.
There are more questions? No? So let's thank the speaker again. Resume at 6 minutes. Yeah.